So some things you're going to hear me say is ground state, excited state. I'm going to talk about quantum numbers, principal quantum numbers, energy levels, quantum mechanics. I want to talk about de Broglie and Heisenberg and orbitals. Essential questions is knowing the Bohr model versus the quantum model. The wave-particle duality and relationships between hydrogen atoms. So some unanswered question from Einstein was, why do the line emission spectra of elements, why were they discontinuous and not continuous? So after Einstein's theory, they did some studies to try to figure out this answer. And the first thing was Bohr. Bohr, we all have talked about Bohr, and he was working for Rutherford. And he proposed a quantum model for just hydrogen. The only thing he did was with hydrogen. And when he did this studies, he found out that he was correct. He correctly predicted the lines for hydrogen. So this is what his model looked like. He said that there in the center is the nucleus, and we know the nucleus contains what? Protons and neutrons. Okay, and he said in that so outside the nucleus, in circular orbits, are the electrons. So this is hydrogen. This is what he studied here. Hydrogen has the nucleus, which only has a proton in there. And we have an electron, and it's circling around the nucleus. And we call that circling an orbit. Okay, it's like the planets. And then there are two different types of states that an electron can be in. It can be in an excited state or a ground state. So a ground state is going to be the lowest potential energy. So it's its lowest amount of energy. And then it's going to move to an excited state. So what happens is it moves up to the excited state, and now it's in this orbital, circling around. Okay?
So it reaches its highest potential?
It's a higher potential, or it's a higher energy.
So the higher the energy, the further away it is from the nucleus?
Yes. The higher the energy, the further away it is from the nucleus. So the ground state is the lowest energy state, and it's closest to the nucleus. For an atom to move from ground state to an excited state, so when it goes from lowest energy to higher energy, it has to gain energy. Okay, so it gains energy in the ground state and moves to the excited state. Okay, so here it's in the ground state. It gained some energy, and it jumped up to the excited state. So now it's in the excited state, and it wants to get rid of that energy, okay? They want to be at the lowest energy that they have. So to get rid of that energy, what happens is that electron will get rid of its energy, and it will fall down to the ground state. When it kicks out that energy, what happens is it emits energy in the form of a photon, which is also light.
So, to go from ground to excited, they have to gain energy, and when they go from excited to ground, they emit energy or a photon.
They lose energy in the form of a photon.
When they're going
Yes, when they're going back towards the nucleus, they lose energy. And they lose that energy in the form of light. So all the light we see, when we're seeing all this stuff, it's from these electrons losing energy and going back down to ground state. Okay? Any questions over that? Okay. Bohr's model. He said that we have 7 orbits. So there are 7 orbits. Orbits. And they called those quantum numbers. So you could have a quantum number of 1, 2, 3, 4, up to 7. The further your orbit is away from the nucleus, the more energy that's out there. The more energy you're going to have. Why is that? Because because you have the positive and the negative, and that negative wants to get back to that positive. Okay? He doesn't have anything to counteract that positivity or that negativity out there. Okay. So, hydrogen just had 1 electron, and so when it's when it's in ground state, it's at N1. When it moves to excited state, it goes to N2. Okay? So that second orbit. And this is kind of what it looks like. You don't have to. The biggest thing I need you to know is that you have the ground state versus the excited state. And it can, if you have this huge atom and you're in N1, you're in an electron in N1, that electron can move all the way up to N7. Okay? And when it drops down from N7 to a ground state is just a lower energy state. It doesn't have to be going all the way back from where it came. It can go back to N1 or N5 or N6. All right? It's just going down to a lower energy level, lower than where it was.
What if they go from another, so if they go in or out, whether it be to a higher or lower state, they stay in that photon?
Yes. But if they're going in towards the nucleus, they're emitting photons.
What if they go outwards?
If they're outwards, they're gaining that electron, or they're gaining that energy. They have to gain energy to move out. Remember, to move away from that nucleus, you've got to gain energy because that electron wants to be by that nucleus, and so it's got to get energy to get away from the nucleus. They're all doing it. They're all moving at the same time. It's not just one electron doing it. All these electrons are continuously doing this in the atom. So Bohr's model didn't talk about the other spectral lines of the other elements, which accounted for other behaviors. Okay, so we had to come up with something else. So they did further studies on Bohr's model. All right, so all you need to know about the limit is it doesn't account for anything else but hydrogen. Bohr's model is only about hydrogen, nothing else. That's the big takeaway from this slide. Bohr's model is about hydrogen and nothing else. So we have this guy named de Broglie. You just need to know that he existed. What de Broglie said, or thought, that if waves can act like particles, could the opposite be true? Could particles act like waves? Okay? So this is what the quantum mechanic model, okay, looks like. Is you have these particles or these waves, and everybody knows what a wave does, but we're not in straight lines. An atom is circular, so these do circular, okay, around the atom. And we have these wave-like behavior, and they're in whole numbers. You can't have half of a wave. It has to be a whole number wavelength. So they are going from this, the nucleus, with the 7, 1, 2, 3, 4, 5, 6, 7 orbits out there, okay? So now, these aren't orbits. They aren't a set area. You have, rather than something like this, you have these little areas out here. Okay? So these are orbits, like the planets around the sun. What they're going to end up calling these are orbitals. Do not get those confused. An orbit is a set path. An orbital is not.
Wait, why is the first one 3 wavelengths? 3 wavelengths.
I don't know. Because there's 3? 3 wavelengths. Yeah, a total of. There's the one, oh, I don't know.
Divided by 2. Divided by 2?
There's the one circular one, which is a 1 wavelength, and then there's the other one, which is 2, and then the other red one that's 3.
Well, that doesn't explain the second one.
The second one right behind it,
Yeah.
you've got 4 of those red lines in there. Wait, hold on. 1, 2, 3. Oh, yeah, there's 2 of them divided by 2. Yeah, 3 wavelengths. Okay. So he came up with this equation. You don't have to write this equation down. But now he's talking about mass, okay, and velocity. It's impossible to notice the wavelength of a fast-moving car, but it can for an electron moving at the same speed. I don't know. That's kind of worded wrong. Okay, so de Broglie came up with this whole equation, and then we came around and he said, oh, we're in these little waves around the nucleus. Rather than orbits, we are now in orbitals. Thank you. And he came up, and then what happened was Heisenberg was like, well, we don't know where these things are. Okay, and so what Heisenberg said, basically this, you need to know that Heisenberg said that you can know the velocity of an electron. You can know the position where that electron may be, but you cannot know both at the same time. You cannot know the speed and the position at the same time. You can know one or the other. Yes?
So did we just write down
The Heisenberg principle, yes. Okay. So, anybody in here watch Breaking Bad?
Oh, I did.
What was his name?
Oh,
What was Mr. White's name? His drug dealer name?
Something like German,
Heisenberg. It's Heisenberg.
Oh.
So Heisenberg. You can either know where Heisenberg is, but you don't know his speed, or you know his speed, and but not where he's at. So it's an uncertainty. So that's why he called Heisenberg, because nobody knew who Heisenberg was in Breaking Bad. Uh-huh.
You said American Dad.
Breaking Bad.
Oh, I heard American Dad. I was like, what?
Oh. So all these guys, really, really smart, Heisenberg, de Broglie, Einstein, Rutherford, Bohr, all of these guys were working on the same project during the World War II. So, there you go. Really, really smart gentleman. So we can just know the probability. And then Schrodinger. Anybody know anything about Schrodinger? Schrodinger's cat. Okay. Schrodinger, he just applied this to other elements. And he said that we just know the probability of finding an electron. And we call this the quantum model. The probability of finding an electron is quantum model. Whereas Bohr's model, you're saying we're circling around that orbit all the time. Quantum model, we just know the probability of where that electron may be.
So, what did
Schrodinger did the quantum model.
And that's all I know.
And that you know the probability of where an electron may be. So really the first 3 slides, the whole Bohr stuff is you need to know by tomorrow. Yes?
So you write the quantum mechanical model?
Schrodinger equals quantum mechanical model, which equals probability of an electron.
Could you just put quantum model or do
No, you can do quantum model.
So do you watch Breaking Bad?
I used to.
So could you like really just like being a chemistry teacher, could you really make math?
I mean, if you had all the products, but they're probably not going to let you buy all the stuff that,
So I'm just curious, like,
But Coach Curtis always says, just getting quit.
Okay, so this is what the quantum model looks like. We went from looking like the orbital to this. So each one of those dots is the probable location of where an electron may be at any given time.
How do we draw that?
I have no idea. This is called a density map. Do you see where it's really dark towards the middle?
Yeah.
What's in the middle?
Atom.
The nucleus. Okay, where does the electron want to be?
Outside.
He wants to be by the nucleus. Okay, so all that dark area is the probability of where you're going to find. That's the most probable location where the electron is going to be, and that is really close to the nucleus. Now there's a boundary. The electron just can't go wherever it wants to go. There's a certain amount how far away it can get from the nucleus. Okay.
what did that guy do? Find out about the shells? So like electrons can like 2 electrons per shell. Alright. So they call shells?
Shells, yes.
I was just curious.
That's what we're about to talk about.
So why are they probable to be around the nucleus?
Hold on. Okay. What?
Why are they more probable to be around the nucleus?
Because the nucleus is positive and they're negative, so they attract. Okay? So the principal quantum number, the principal quantum number is just the major, so this is what I need you to know right here. The principal energy level. Oops.
Which one do you think about?
Hold on. I'm going back there. Principal energy level. That is the outer, if we were thinking of the Bohr model, that would be each one of these. There are 7 of them. So principal energy level would be this 1, 2, 3, 4, 5, up to 7 of them. Or you call them shells. Okay, there's 7 shells. Yes?
So 7 shells, that's all we have 5 nucleus. That's not the same values.
All atoms only have 7 shells.
All atoms are the same.
Energy levels. Okay, within these shells, we have different energy levels. Or sublevels. Sublevels. So each one of these is a level, and inside each one of them is a sublevel. And those sublevels are further broken apart into orbitals. Yes?
So the ones on the farthest shell always be in the excited state?
The ones that are going out there are going to be in the excited state, yes. It will, or they're going to have the most, not excited state, they're going to have the most energy. Okay. So you have these 7, remember we have the 7 shells? So we have the 7 shells, and each shell has some sublevels or subshells. So there are 4, and not all of them have every one of them. There are 4 different sublevels. So I need you to write these down. The smallest sublevel is S, or orbital. The smallest orbital is S. And S is sphere. That's the shape of it. All these orbitals take on shapes. The S orbital is a sphere. Okay? So it has that sphere, and there's 2 electrons. So each S suborbital, so S suborbital, there is 1 like orbital within it, so this is an orbital, or let's do this. S orbital. There's only 1 suborbital. Each suborbital can hold 2 electrons. So each S suborbital can hold 2 electrons. So you have an electron here and an electron there, and going around. The next orbital is the p orbital. And the p orbital, if we're looking at a x, y, z axes, the p orbital looks like this. You have 1 suborbital on the y-axis, you have 1 suborbital on the x-axis, and you have 1 suborbital on the z. So there are 3 suborbitals in the p. Each one can hold 2. So how many electrons can the whole p hold? If there are 3 suborbitals, and each suborbital can hold 2. So we can hold a total of 6 electrons. D. After the p suborbital, there is D. And D, there are 1, 2, 3, 4, 5 suborbitals. 5 suborbitals. For a total of how many electrons? Each one can hold 2. Can you please put the phone away? 10 electrons. D, I kind of like the dumbbell. If you take 2 dumbbells and put them apart on top of each other, that would kind of look like what it would look like. Make a cross or something. That's what the orbitals look like. And that's an electron following that path around the x and y axis. Yes? Did you have a question, Micah? No.
I am.
I just don't.
Yeah, right. You're playing games.
Yes, 100%. But I don't even know what to ask.
The diagram.
Yes.
The S
So do we have to know how many orbitals?
I would know S, P, D, F. I would know that each one, S has how many suborbitals? 1. P has how many suborbitals? 3. D has how many suborbitals? 5. And F has how many suborbitals? Count them. 7 suborbitals.
Hey, that's pretty easy.
Each suborbital can carry how many electrons?
Oh, so it's just the odd numbers. 1, 3, 5, 7.
Yeah.
14 electrons.
Okay, so 3. See that? Yeah. That's S orbital. And it's inside the S orbital, the sphere.
So there's really
And
just
it can hold
4
2 electrons.
4. S, P, D, F.
And then the other,
And then there's
They're broken apart into further
and further ones just make them 7.
to make 7.
And they can carry
2 each.
electrons
Yes.
which makes it
How would you draw D orbital?
D, I don't know. You don't have to draw it. I'm not going to say which orbital is this.
Oh.
I mean, if I say which orbital is this, and you see 5 of them, you'd go D. Or if I gave you all the shapes of F, which F I think of as a flower. We continue on. I said each can hold 2 electrons. All right, so this is what it represents on the periodic table. Look at the periodic table. If you're looking at the periodic table, and like I said, this is the P block too. Let me get my iPad here and make these notes here. You see that this is the P block. Oh, this is also the P block. So the P block is all the way over here. The helium, oops. Why is it not? This is part of the S block. So that's the only weird part there.
Can you leave that up for a minute?
Yeah, because I'm about to go over it. Okay, so S, P, D, F. The last electron in each element ends. So if I'm in the S block, my very last electron is going to be in the S suborbital. If I'm over here in the P block, my very last electrons are going to be in the P suborbital. If I land in the D block, all my electrons are going to be in the D. My last electrons will be in the D suborbital. Yes?
Where did they come up for the letters for this?
I have no idea.
Is it like they make like this
They
S
probably,
sphere? Is it like
they probably come after something like that. Yeah. Okay. The next thing I need to see is the following. How many electrons can S orbital hold? 2. How many columns are in the S block? 1, 2. P. How many electrons can the P suborbitals hold? 6. How many columns are in the P suborbital? P block? 1, 2, 3, 4, 5, 6. The D block can hold how many, or Ds can hold how many electrons?
10.
10. How many columns do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. F. How many do we think there's going to be in the F? 14, and there is. So it's all starts to make that this periodic table is so beautiful. It's just there's so much information there. Okay, so what I'm going to say is by the end of next week, I'm going to say, hey, Luke, tell me the address of all the electrons for boron. And you're going to be able to tell me where each electron is in boron.
Oh my God.
So, okay, any questions over that? This is,
Yeah, don't move it.
okay, I'm done. I'm going to stop my recording and